0.1 m solution of a weak acid HA was prepared by diluting an appropriate amount of the VPO weak acid of 25 cubic centimeters. So there is 0.1 m solution of HA, and it is diluted up to 25 degrees Celsius, sorry, 25 cubic centimeter at 25 degrees Celsius, and the pH is given as 3, and consider the dissolution of the acid here in water and calculate the dissociation constant Ka. So these are just very simplest theory questions. So I will use the board to explain this, okay? So we have HA that is going to react with water in an equilibrium, forming H3O plus and OH minus. So Ka is equal to H3O plus concentration times OH minus concentration over HA concentration. So we have to find this Ka. The easiest thing is they have given pH. So you can use pH, which is given as 3.0. So pH is equal to minus log H plus concentration. So 3 is equal to minus log H plus concentration. So H plus concentration is minus 3. I will write as this. Log H plus is minus 3. So H plus concentration is antilog minus 3. Okay, so which is 1 into 10 to the power 3. So if this is 1 into 10 to the power minus 3, so this is also going to be 1 into 10 to the power minus 3, because according to this equilibrium, same amount of OH minus should be given to the system. So HA is 0.1 m minus some x, which is negligible, is small. So your Ka expression is 10 to the power minus 3 into 10 to the power minus 3 over 10 to the power minus 1. So you can get 1 into 10 to the power minus 5 mol dm minus 3. So this is your Ka expression. So you have to show this equilibrium, write down the Ka expression, and find pH and say H plus concentration is 10 to the power minus 3, which is obtained here. Then you plug the value and find Ka. That's it. Okay. Next one. So normally they will give Ka and find to pH, but here it is the reverse. They have given pH to find Ka. Next part. So we have done this one. A dilute solution of this weak acid was titrated with strong base BOH, and it was found that the pH of the titration mixture after reaching the equivalence point was 9. Calculate the concentration of salt. So basically, when you have this reaction, HA reacting with BOH, like sodium hydroxide, so what is going to happen? So Ba and water is formed. So this is our salt, BaOAb, anyway. Okay, and they have given so the equivalence point pH is given, right? Equivalence point pH is given as 9.0. So calculate the concentration of salt. That is what they are asking. So anyway, but the only thing that you have to understand here, I will stop sharing, is this. Now, at equivalence point, you will not have this one and this one. The only thing that you have here at the equivalence point is the Ba salt. So basically what is going to happen, Ba is going to give you the anion and cation form. So which is B plus and A minus, and this A minus, which is derived from the acid, is going to react with water to form Ha plus OH minus, which is the base hydrolysis. Okay, so this is the salt hydrolysis that we are going to expect at equivalence point, right? Because if you know the concentration of this one, this is the concentration of this one, and this is the concentration of same A minus. So this is a base hydrolysis of the conjugate acid. This is HA for Ka. So A minus hydrolysis Kb. So Kb is equal to Kw over Ka, which is 10 to the power minus 14 over 10 to the power minus 5, and this is 10 to the power minus 9. Okay. So how do you write Kb for this one? So Kb for this one is concentration of Ha or H minus over concentration of A minus, which is our salt concentration directly. I can put salt concentration directly because A minus concentration is equal to my salt concentration, because this is at equilibrium. Okay, so Kb is known. This is 10 to the power minus 9. Ha and OH minus concentration you can calculate like the previous method because they have given pH is 9. So pH is 9 means your H plus concentration is 10 to the power minus 9 m. So your OH minus concentration here using Kw value, you can calculate that as 10 to the power minus 5m, because H plus times OH minus is 10 to the power minus 40. So this is 10 to the power minus 9. So H plus, you know. So OH minus is 10 to the power minus 5. So this should be 10 to the power minus 5 times 10 to the power minus 5 over salt concentration. So my salt concentration is this 10 to the power minus 10 here, salt 10 to the power minus 10. This is 0.1. Right? So this is typically accepted because this is 0.1 concentration. So if you use same equivalence point, so 1:1 ratio. So the salt is more or less same amount is formed. So if you use same volume, so could be 0.1. This is the concentration of the salt. Okay. So this is also the other way around. So normally they give, we are mixing this amount of acid and base and you will have the salt and find the final pH. But here they are telling at equivalence point, they have given the pH and you need to find the solution for the salt concentration. Okay, so I will check with this one. Yeah, it's okay. Great. Last one. So this is also done. The above titration mixture was diluted 100 times by adding distilled water. Okay, calculate the pH of the diluted titration mixture. So what is going to happen here when you dilute it? So you have your salt concentration as 0.1. So basically you dilute 100 times means your concentration is going to drop by 100 times. So your salt concentration is 0.1 m. So you divide it by 100. So this is 10 to the power minus 3m, right? So if this is 10 to the power minus 3m, this is also 10 to the power minus 3m, this is also 10 to the power minus 3m. Okay, so at this point, you know the concentration of my salt. So this is 10 to the power minus 3m. So according to this equilibrium, I am going to get a new equation, right? So Kb I know, that is 10 to the power minus 9. H and OH I have to calculate. So I will take this as x maybe. So this is x squared. Over salt concentration is now 100 times diluted. So earlier it was 0.1 by using the calculation of pH. Now here you have to calculate. So this is 0.001 now. By 100 time dilution, it becomes 10 to the power minus 3. So according to this, when I do the calculation here, I get x squared, which is my OH minus concentration, squared equal 10 to the power minus 12. Okay, so I get OH minus concentration as 10 to the power minus 6 cent. So if you know OH minus, you can calculate H plus concentration. It will be 10 to the power minus 14 over 10 to the power minus 6, and it is 10 to the power minus 8. So pH is equal to minus log H plus concentration, which is 10 to the power minus 8, and pH is here 8.0. Okay, so you understand what is happening when you diluted 100 times. So when you dilute 100 times, the pH is dropped by 1. It is what normally happens with the salts. Okay, but when you have like strong acid, yes, still you're going to get a pH value difference of 2, but here there is only 1 because this is not a complete dissociation. This is in equilibrium. Okay, so you can show the calculation as this. These are not hard. Okay, these are just theory questions. So this is also done, right? So we are going to move to the final part here, not final, in fact, part B. So you have given a small piece of information. So AgBr is a solid, which is a pale yellow color, so you know that. Sparingly soluble salt in water. Its solubility product KSP is given. Calculate the concentration of Ag plus in a saturated solution. So these are very simple, straightforward calculation that you should know up to now. So I will just erase the board and I will do it in my. So I will share the screen again. So you know there is AgBr, so AgBr should be in equilibrium like this. So we have AgBr. So AgBr solid will be there. This is in equilibrium with Ag plus, and Br minus. So you have to put the physical state. So this is aqueous. This is also aqueous. So you have given the KSP value, right? So the KSP value is 5 into 10 to the power minus 3. So you can write KSP of AgBr solid. AgBr solid equal Ag plus concentration, basically. You have to write aqueous here, put the all physical state, and Br minus aqueous. Okay. So you can write let the solubility of AgBr be X, then solubility of Ag plus is also X, this is also X, right? So your KSP expression becomes 5 into 10 to the power minus 13, put the units, is equal to X squared. Then you can find the solubility. So you can write this as 50 into 10 to the power minus 14, because to get the root, it is very easy by making this 10 to the power product as an even value. So 50 root is roughly around so 7 squared is 49, so it could be like 7.1 maybe times 10 to the power 7 mol minus 3. So this is the solubility of AgBr. according to this calculation. Okay, so this is a first principle. When you have given the KSP, how to calculate solubility. So this is straightforward. Okay. Solid AGBR together with 100 cubic centimeter of the solution described in part 1. So part 1 means this is our saturated solution. So this is a saturated solution of AGBR in part 1. Okay, this is a saturated solution. Solid AGBR is added together. Solution part 1 was placed in a beaker. A volume of 100 cubic centimeter of distilled water was added to the beaker, and the mixture was stirred well until the equilibrium state. So what they have put here is they have put here some solid AGBR, and they have added water as well. 100 cubic centimeter of water plus some solid AGBR. At this stage, some solid AGBR was still left at the bottom of the beaker. So there is some, okay, so still the solution is saturated, right? What could be the concentration of Ag plus in this solution? Explain your answer. So initially, in the first question, you calculate the solubility of AGBR here for the saturated solution. So this is a normal saturated solution. But in the second part, you add some solid AGBR and you add dilute water and you shake it and you do all the things and you allow to reach equilibrium. And if you see at this stage, some solid AGBR is left at the bottom. What does that mean? Can you tell me what does that mean? Can you suggest what does that mean? Can someone suggest what does that mean? Because after you do all these things, adding AGBR and you add water and do all the things, still if some AGBR is remaining, what does that mean? Can someone tell what does that mean? I am waiting for your answers. No answers, so I will explain. So the idea is this. Here we calculated the solubility of AGBR by using KSP because it is a saturated solution. So here, although you add some solid AGBR, you add water, and if you still see some solid that is left in the AGBR container, which means there is solid AGBR, which gives you the idea the solution is still saturated. So if the solution is still saturated, what does it mean? The solubility of AGBR is still same because it is not going to change, because here we just get the saturated solution, and in the saturated solution the AGBR solubility is 7 point something into 10 to the power minus 7 m. Okay, so this has to maintain KSP. Either you add some additional solid here, so the solubility is not going to change. This is a supersaturated solution. That is why additional AGBR all get precipitated out in order to maintain the same solubility in the solution. Okay, so what could be the concentration of Ag plus? The concentration of Ag plus is same as in part 1. So it is 7 into 10 to the power minus 7 m roughly. So what is the reason? The reason is after adding AGBR, if some solid is remaining at the bottom, still the solution is saturated so that the solubility is same. That's it. Because The equilibrium has to maintain Ksp at the same temperature. That's the idea. Okay, so this question is very, very long, but the answer is very simple. Okay. Using a suitable calculation, predict the observation expected when 10 cubic centimeter of AgNO3 and 5 cubic centimeter of 6 into 10 to the power minus 4 NaBr solution are mixed. So here it is very similar to our RQ. So what you can give, you can calculate RQ or ionic product. You can calculate ionic product. So first what you have to do, first find the Ag plus concentration, because when you are mixing, the total volume is 15. So here there will be Ag plus concentration of 10 into 1.5 into 10 to the power minus 4 times the volume is 10 cubic centimeters. So it can be 10 to the power minus 3 in decimeter, divided by the total volume when you mix was 15. So 15 into 10 to the power minus 3. Okay. In the same way, you can calculate the final initial Br minus concentration. So this will be 5 into 10 to the power minus 3 times 6 into 10 to the power minus 4. This is the number of moles of Br minus used, and the total concentration is 15 into 10 to the power minus 3. Okay, so you can solve and find the concentration of Ag plus and Br minus. So my RQ is Ag plus concentration times Br minus concentration. So you can plug these two values and check this RQ exceeds this Ksp value. So if this RQ value exceeds this Ksp value, you can mention the AgBr will get precipitate. Okay, so you have to mention the observation. The observation, if this RQ value is greater than Ksp, a pale yellow color precipitate was observed. Okay, and if this RQ is less than this Ksp, you have to mention no precipitation was observed. Nothing happens. Okay. In fact, when you calculate, you will see the pale yellow color precipitate could be observed, because this RQ value is going to exceed your Ksp value. RQ is going to exceed Ksp of AgBr. Okay, so you understand the point. Find the initial concentrations, find RQ, and check whether it is greater than Ksp. Okay, so that's the idea. So we are at the final phase of this question. So this is again phase equilibrium, heterogeneous phase. The pressure of the vapor phase in equilibrium with an ideal binary solution is P. So there is an ideal binary solution. Let's say A and B is there for an example. So this is in equilibrium with its vapor. So this is A and this is VB. So the total pressure is given as P here in the vapor phase. The liquid phase mole fraction of the two components are X1 and X1. So for A, we will take as X1 and this we will take as X2. The saturated vapor pressures are given P01 and P02. Show that X1 is this. So you all know, okay? So if you know the vapor mole fraction and the saturated vapor pressure, you can use Raoult's law. So basically you can write, let's say P1, which is the parcel pressure in here. P1 is equal to P01 X1, right? And in the same way, P2 is equal to P02 X2. But you need to calculate X1. So instead of X2, you know X1 plus X2 equals 1 because only A and B there. So the mole fraction, sum of mole fraction should be equal to 1. So you can write x1 is equal to 1 minus x2. So here my equation here will be P2 naught, times 1 minus, I have to mention here this is as x2, so this is x1. 1 minus x1. This is my P2. Then you have two equation P1 and P2. You can add these two. So 1 plus 2 will give you P1 and P2. This is the partial vapor pressure of A and B here for an example. So this should be equal to the total pressure that is given as P. So P1 plus P2, which is equal to P, sum of these two, P naught 1 x1 plus P naught 2 1 minus x1. So now you can rearrange this and you will get this equation, because the only thing that you have here is P naught 1 and P naught 2, which is given here. So you can find x1 here and you can rearrange this particular equation to get this x1. That is very straightforward and simple. Okay. So I have mentioned this many times. Anyway, if you do these equilibrium questions, space equilibrium, you have these two equations, Dalton's law and Raoult's law. Even here, you don't have to use Dalton's law to explain this. The only thing is Dalton law that I have used here is partial pressure of these two is equal to the total pressure. That's it. The pressure of the vapor phase in equilibrium with a binary solution containing methanol and ethanol is given 4.5 into 10 to the power 4 Pascal at 50 degrees. At this temperature, the saturated vapor pressure of methanol and ethanol are 5.5 and 3.0. Consider that the solution behaves ideally. So this is a binary ideal solution. Calculate the mole fractions of methanol and ethanol in the liquid phase and calculate the mole fraction of methanol and ethanol in the vapor phase. Okay, so we will do this calculation on the board. So we have a binary solution where methanol and ethanol is in equilibrium with its vapor. And pressure is given. So I will just. So this is 4.5 into 10 to the power 5 Pascal. You see it? Ten to the power 4. And methanol, I will take as P naught M. P naught M is given as 5.5 into 10 to the power 4. And P naught E is given as 3.0 10 to the power 4 Pascal. That's it. Okay. So I have to calculate the mole fractions in liquid and vapor phase. So I will take this as XM and XE in the liquid phase. XM liquid and XE liquid. And here I will take as X naught M gas, X naught E gas. Okay. And the total pressure is given. So the first thing that you need to understand, this is total pressure. So PT is equal to P methanol plus P ethanol. So 4.5 into 10 to the power 4 Pascal is equal to P naught methanol plus P naught ethanol. So if I write down according to the Raoult's law, my P methanol will be P naught methanol, which is 5.5 into 10 to the power 4 times X methanol in liquid plus P naught ethanol, which is 3 into 10 to the power 4 plus X ethanol in liquid. This is 1. And the other way around that I can write here, this 4.5 into 10 to the power 4 Pascal is mole fraction. Let's calculate here directly. P methanol gas, which is here in the vapor pressure, that is equal to mole fraction of methanol, M X naught M gas times total pressure PT, which is 4.5 into 10 to the power 5 Pascal. And in the same way, P ethanol gas is equal to X naught ethanol gas times PT, which is this one. Right? So you can understand what is actually happening here. Because if I add these two, for an example, here PM gas plus PE gas, you will have X naught M gas PT plus X naught E gas PT. So I have few equations, and here I know these P naught M values and P naught E values. These are 5.5 into 10 to the power 4. This is 3 into 10 to the power 4 Pascal. And here I know the total pressure, which is 4.5 into 10 to the power 4 Pascal, which is my total pressure. And this one I know. So you know all these things. The only thing that you don't know here is XM liquid, XE liquid. And here X naught gas and X naught methanol gas and X naught ethanol gas. Right? So can you find this after this? Very quickly. Because here you don't know these two, XM liquid and XE liquid. But according to Dalton's law, partial pressure of PM is equal to PT times X naught M gas. So PM is this one. You see that? PM is this one. Right? So this one is 5.5 into 10 to the power 4 XM liquid, which is equal to X naught M gas times PT, which is 4.5 into 10 to the power 4 Pascal. Right? So you can cut this one and this one. So XM liquid over XM gas will be equal to 4.5 over 5.5. So there is a ratio 9 over 11. You understand it? There is a ratio of 9 over 11. So if you know this ratio of 9 over 11, where this is liquid and gas, what should be the other one? This is for methanol, and for ethanol, liquid over gas should be 2/11. Okay, because you automatically know that, or either you can calculate this one using this value and this value that you should already know. Okay, then what you have to do, you have to just plug that here in one of these equation and find x in the liquid first, and then find in the gas. Okay, you need to understand that, because here from this relation we get the ratio of the methanol and in the gas and liquid stage. Then you have to just use the only equation that is present here is these two, no other equations left. You have to just use the ratio. Okay, so these are very simple calculations that you can use to do the, because when you know the calculation is easy, then you can do, right? So I will share the screen then. So these two are very straightforward cases, because you know the equation. You have to just plug and find the equation. Based on the above calculation and given information, draw the vapor pressure composition diagram of methanol and ethanol at 50 degrees Celsius. Consider that the solutions behave ideally. So this is not much what you have to do here. So you know already the saturated vapor pressures and everything. So you have to draw the vapor press composition. So you have to mention like X, let's say methanol is 0 here. So then X ethanol should be 1 in this place. And this is composition. You have to write here composition. And here then XM should be 1. And here X ethanol should be 0 here. So when ethanol mole fraction is 1, so this is pressure at Pascal. I have to mention all this. So you know when ethanol is 1, mole fraction is 1, there is only ethanol. So that is the saturated vapor pressure of ethanol. So what is the saturated vapor pressure of ethanol? That is 3 into 10 to the power 4. So you just put something here and indicate that 3 into 10 to the power 4. And when methanol is 1, so its pressure is 5.5. So you can show here as this 5.5 into 10 to the power 4 Pascal. Then you can combine these two using a straight line, indicating this is the total pressure. So the vapor pressure graph of methanol and ethanol can be given like this. In fact, this is enough to show. Okay, and this curve gives you the total pressure. Okay, don't forget that. Not this one, this straight curve. That is what that you have to mention. Others are all okay.